Hi everybody, welcome back to my channel, Theoretical Physics with Mark Weitzman. Today we're going to do another video on electromagnetism, and we're going to do an exercise from the Feynman lectures on physics. So I will just, this is exercise 44-7, and before I do that, I just want to, I'm sorry. I just want to show the book. You can get it anywhere. It's fairly cheap, $15 to $20. It has all the exercises that we used at Caltech when Feynman originally taught the course. The exercises, as I've mentioned before, are sort of uneven. Some are routine, some are good, um, some are hard, a lot are easy, but they're worthwhile going through. And for those who've complained that the Feynman lectures on physics doesn't have any exercises, it certainly did. These were published a couple of years after the Feynman lectures on physics came out. They were in little pamphlet books that were read, and then they've been put all together in these book here. The answers are given, but the solutions are not completely given. Some of the questions do have solutions, but most of them just have answers like a formula or a number. So let's get to the problem today. A metal spherical shell of inner radius A and outer radius B is located with its center at the origin. There is a small hole cut at one point of the shell. A, if there's no charge on the shell, how much work WA is required to bring a charge Q1 from infinity through the hole and to the origin? B, how much work is required if the shell is given a total charge? So let us start to work on this. What we have for A, we have two concentric shells. This is a metal conductor. There's no charge on the shells. The inner radius is A, and the outer radius is B. And we have a charge Q1. Q1 at R equals infinity. And we want to know the work that's required to bring this charge to the center of the shell. Now, if you've never taken any electromagnetism, you might think no work is required. There's no charge on the shell. There's no force on the charge. If I just bring it in, there's a little bit of a hole in the shell. Let's say from here. And this is supposed to be a very small, hole where the charge can go through. So essentially, we're going to bring the charge all the way from infinity through this hole to the origin. But that's incorrect. As if you study electromagnetism, you know that this charge will attract charges on the shell. If this is positive, let's assume Q1 is positive. It will attract negative charges to the outside of the shell, and the inside of the shell will probably have positive charges, and then it will reverse. So there will be forces on the charge, and so the first I want to say is this: if you notice, this corresponds to Chapter 8, electrostatic energy, and that tells you right away use energy differences to solve the problem. Do not use methods like images and forces and and calculate work. I'm not saying this won't work, but it's a lot hard. Um, if it was, I'll do it for an example. Um, I'll do it for an example where it's just an infinitely thin shell. It's just a sphere. So if we just had a sphere like this, and we were bringing a charge Q1 at R equals infinity, and this is like the center of the sphere, and we were bringing it in here, then we could calculate it, and I'll do that calculation just to show you why you don't want to do it. If here you only have one image charge, there's going to be a Q, there's going to be like an image charge here, Q prime. You can calculate the force, you can integrate to calculate the work, and that's what we're going to do. But it's not as easy as using energy differences, and it's not when you have a shell, you're going to have many image charges. You're not just going to have one image charge, because you have two surfaces at zero potential, so you're going to have several image charges, and it's going to get complicated. And there are divergences, and handling the divergences not going to be trivial. I'm saying it can be done, but let's not do it. So I don't want to draw this diagram again because I'm not very good at drawing. So let me just show you. This is from an earlier chapter in Feynman. I'm sorry. Here, this is in chapter 6 where he does the image charges. And now we have a point charge Q. And an image charge will be located, let's say this is at distance b from the center. There'll be an image charge a squared over b, and a q prime. The charge is minus a over b q. So using this image charge, we can solve the problem. Also note that although Feynman doesn't give the diagram, if the charge is inside the sphere, the same formulas apply. The image charge will then be outside the sphere, and these exact formulas will apply. The only difference would be if you're calculating the surface charge density, it'll be a little different because the normal will be in a different direction. But we're not going to be calculating that, so we don't need that. So you have to be careful here with the integrals and the signs and everything. Let's just get an idea. Since the charge and the image charge have opposite charges, there's going to be an attraction. So there's going to be a force toward the sphere when it's outside, and you're going to have to exert an applied force opposite to that force to bring the charge in quasi-statically. So your force is going to be to the right, the applied force, and yet you're moving to the left, the displacement is to the left. So we expect the work done when the charge is outside the sphere to be negative. When it's inside the sphere, the charges will still, charge and the image charge will still attract each other, but now the force is going this way. The applied force is now going to be to the left, and that's in the same direction as the displacement. So we expect the work done inside the sphere to be positive. So let's just write down the integrals outside the sphere. The work done on the charge Q outside, I'll use O for outside, is equal to the integral from infinity to the radius A and we always have our 1 over 4 pi epsilon 0 because Feynman uses MKS units. Okay, let me go back to the iPad. Hopefully you'll keep this diagram in mind. The image charge the force, as I said, will be, we're going to have to apply them when it's outside. The force is going to be this way, so it's going to be positive. And the magnitude is going to be A over R times Q. That's the magnitude of the image charge times the charge. We're just using Coulomb's law here. We're integrating from infinity to A of dr, and I'll be elaborate more in a second. And the distance between them, this distance over here with Q prime, is Q squared over R, and Q prime is equal to minus A over RQ. I'm using R for B in Feynman's diagram because we're going to be integrating. And it's R minus Q squared over R is the distance squared. So this is Coulomb's law. Notice in this integral, since we're going from infinity to A, everything in this integrand is positive, but dr is negative because we're going from infinity to A. So that's why this is, in fact, this will be negative. And inside the sphere, we're going to integrate from A, when we get there, to 0. 1 over 4 pi epsilon 0. Now the force, the charge is going to be attracted from the center of the sphere when it's inside. The image charge is here, but they're still opposite, and it's going to be attracted this way. So the force is going to be negative, and the applied force that we have to do is positive and in the same direction as dr. So we're going to have a, since the force is to the left, we're going to have a negative there. We're going to have the charge Q inside, the image charge AQ over R outside, dr, R minus Q squared over R squared. So this will be positive. Now, in fact, both of these quantities diverge, but they're really the same quantity, so we can match them up and not worry about the divergences. And we'll see that the end result will be 0 as we would expect. The total work will be WQ0 plus WQI. The integral from, this is equal to the integral from infinity to A, 1 over 4 pi epsilon 0, A Q squared R over R squared minus A squared squared. I just took the 1 over R in the numerator and put another 1 over R there, which I cancel by an R, and then I have R squared in the denominator, which I bring inside, which is multiplied by R. It just simplifies everything. So this over here, this should be A squared, sorry. A squared over R. Just see if and on the inside it's the same thing. A squared over R. Okay. And then I have a minus, because we have a negative sign in the integrand, minus the integral from A to 0, 1 over 4 pi epsilon 0, A Q squared R dr divided by R squared minus A squared. Okay. Now, you can do these integrals directly, but as you'll see, they're divergent because you're going to have an R squared minus A squared in the denominator, and when you substitute R equal A, it will diverge, and same thing here. So we don't need to get into the divergences and everything because the integrals are exactly equal and opposite. And over here, we'll make a substitution x equal r over a in both integrals. So we'll get the integral w total is equal to 1 over 4 pi epsilon 0 a. This is just routine substitution. The integral from 1 to 1. I'll change the variable to x dx, x squared minus 1 squared minus 1 over 4 pi epsilon 0 a. The integral from 1 to 0, x dx over x squared minus 1 squared. I definitely left out the q squared. So there should be a q squared here and a q squared here. And now I just make the substitution in this integral. Just this integral, I do x goes to 1 over x. And now we're going to get w total is equal to q squared 4 pi epsilon 0 a. So now I have 1 over x times minus 1 minus dx over x squared. And then I have 1 over x squared minus 1 squared minus the integral. Sorry, I left out the integral. So now since we're going x to 1 over x, the integral is from 0 to 1 minus the integral from 1 to 0 x dx. I'll write this as 1 minus x squared squared, same thing. And now when you bring all the x's in and simplify it, you just get this is equal to q squared over 4 pi epsilon 0 a minus the integral from 0 to 1 of x dx 1 minus x squared squared plus the integral from 0 to 1 x dx 1 minus x squared squared. And this is obviously equal to 0. These just cancel. So you can see that they have the same kind of divergences at x equal 1. And so it's easy to show, we could be more rigorous, but it's easy to show that these cancel exactly. So when we do the solution for the spherical shell, we'll see that the answer is also 0. So that's comforting. Now, let's just do it using energy. So initially we have a charge Q1 over here at infinity. And we have some kind of shell very far away. So far away that it doesn't affect the problem. And then the potential energy, I'm going to use the symbol U because we're using E for the electric field. This is what Feynman uses. And we're going to get the formula that he uses, the integral over all space E dot E dV. And this is equal to the integral from r equals 0. It diverges, but we're not going to worry about the divergences. Q1 squared over 8 pi epsilon 0 r squared dr. So the effect of the spherical shell is just negligible because it's so far away. We're just determining the energy in the initial state, and it's basically the energy of a point charge which does diverge. We could give it a finite radius and deal with convergent quantities, but it doesn't really matter. Now this was our initial. Now let's do the final. So finally we're going to have a charge Q in the center. a metal shell. And now UF, we'll use the same formula, epsilon 0 over 2, but now there is an electric field inside of the spherical shell from the charge Q. There's no electric field here, E equals 0. Essentially, we have negative charges on the inside, which cancel, and by Gauss's law, the electric field is 0, and then we'll have the same positive charges on the outside, which will give us our regular Coulomb law. So now we're just going to get the integral of epsilon 0 to 2, the integral from r to 0 of e dot e, the relevant e, plus the integral from a to b, e dot e, dv. I'm going to apply this to all of that, but here this is going to be 0, e equals 0, and then the integral from b to infinity of e dot e dv. So that's going to be our final thing. And of course, it's very easy to, the formula, it's very easy to see. We'll apply the same formula. UF is equal to the integral from 0 to a of q squared dr 8 pi epsilon 0 r squared plus the integral from b to infinity q1 squared, should have q1 squared, q1 squared dr over 8 pi epsilon 0 r squared. Remember, what we're doing is we're just using Coulomb's law, which is a 1 over r squared for the electric field. When we square it, we get 1 over r to the 4th, but then we have the dv measure over here, which is 4 pi r squared dr. So that's how we get this. And you can just look at this integral and you see that it's the same thing as ui minus the integral from a to b q1 squared dr 8 pi epsilon 0 r squared. So the work that we have to do, our work is simply uf minus ui is equal to minus the integral from a to b q1 squared dr 8 pi epsilon 0 r squared, and this is equal to q1 squared over 8 pi epsilon 0 1 over r evaluated at a and b. Remember, when we take the derivative of 1 over r, we get minus 1 over r squared, so we have that minus sign conveniently there. And so this is equal to q1 squared 8 pi epsilon 0 1 over b minus 1 over a. And that is our answer, and luckily it agrees with the answer at the back of the book, back of the exercises for the Feynman lectures on physics. Also notice if we set b equal to a, we get 0, which is what our previous calculation gave when we did it directly using the method of images and forces. The second problem is just if we put a total charge of Q2 on the shell. This is easy to do. We use superposition. So forgetting all about induced charges and all that other stuff, we're now just going to take the case where we have a shell, inner shell, and an outer shell. And we have a total charge of Q2. Q2 will put itself on the outside of the shell. Inside the shell, there'll be no electric field here, and there's no charge inside, so there's no electric field inside. So we simply take the potential energy of this Q1 charge at infinity, and it's just going to be Q1, Q2. It's our usual formula for potential energy. So WB is going to be equal to WA plus Q1, Q2, 4 pi epsilon 0 B. Because we have a charge, the outer radius is B. And so we bring that charge to the outer radius B and we get our usual potential energy formula. Okay, so that's all I have to say on this. It just shows how if you didn't use energy to solve the problem with the shell, you'd be in trouble. You might be able to get it done using a few images and doing the integrals and putting them together carefully like I did with the single sphere, but it's going to be much harder. So I will see you next time, and thank you very much for watching. Bye-bye.